Okay. So as we go into looking at coordination chemistry, let's first review Lewis structures before we start to talk about that. Okay, so the basic process for drawing a Lewis structure, right, is we're first going to count the total number of electrons in our compound, and that is valence electrons, right? Two, we're going to draw a skeleton structure, and we're going to draw two electrons in between each atom, and then we're going to distribute the remaining electrons and making sure we account for the octet rule and also minimizing the formal charge on atoms. So let's take an example of tetrafluoromethane. Okay, and so we have 4 valence electrons for each carbon and 7 valence electrons for fluorine, and so that's going to be 28 plus 4 is 32. Okay, now, so that gets our total electron count in the first step here. All right, so the next thing we're going to do is we're going to draw a skeleton structure. We're going to pick a central atom first of all before we do that, and so with some kind of practice in there, we can usually identify a central atom pretty easily. And so in this case, we're going to start with carbon, and then we're going to have the fluorine atoms surround carbon like this, okay? So this gives us kind of a layout of the atoms within the molecule, and then we're going to have a minimum of 2 electrons, right, in between the central atom and each so-called pennant atom, where the fluorine, in this case, is acting as a pennant atom. So we draw 2 dots here, okay, between each pair between the carbon and fluorine atom, okay? And so that accounts for at least a single bond between the carbon and each fluorine atom, okay? And so from there, we need to distribute our electrons. And right now, what we have is 1, 2, 3, 4, 5, 6, 7, 8, okay? So that means that we have another 24 electrons still to distribute, okay? Now, we have to satisfy, so for the most part, we're going to satisfy the octet rule when we draw these Lewis structures. And so what we see is that with carbon, we already have an octet surrounding the carbon atom. So that means we can't distribute any more of the 24 remaining electrons around the carbon. So in this case, it's going to end up around the fluorine atoms, okay? And so we have 4 fluorine atoms and 24 electrons, so that means we can distribute 6 electrons each to each fluorine atom. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and so again, we've now distributed the remaining electrons. We have 32 showing. So 1, 2 plus 6 is 8. 8, 8, 8 times 4, right, is 32. So we've accounted for all the electrons. Now remember, we didn't add any of the carbon, so the carbon still is following the octet rule. So is each fluorine atom. So each fluorine has 1, 2, 3, 4, 5, 6, 7, 8 surrounding it, and that's true for all of them. And we don't have any formal charge in each of the atoms. So this gives us some idea. So this suggests that we have a valid Lewis structure for so the tetrafluoromethane. Okay, and so we can redraw this, right? Where instead of, for instance, instead of drawing 2 electrons right in between each carbon fluorine atom, we can draw a line like this. So this can be kind of like a shorthand. But we're going to remain leaving the lone pairs on each fluorine atom. Okay, and so we can also depict our structure like this for tetrafluoromethane. But as you know, in this Lewis structure, all we've done is we've accounted for distributing the electrons. We have not, however, accounted for the geometry. And so we would need to use VSEPR in order to take our Lewis structure and attempt to predict what the geometry would be of this molecule. In that case, right, we would expect this to have a tetrahedral geometry based on VSEPR. but we will not cover that, but I strongly suggest you review that from general chemistry.